Thank you for attending our WAVEtek webinar. I'm excited to speak with you about a topic I've worked on and believed in for many years. Today, we're going to talk about fundamentals of large-scale microwave food processing. This is the first of a 10-part, 20-minute series that will cover the content of a two-day in-person workshop that we offer throughout the year. Today, I'll talk about some general misconceptions about microwaves and how they operate, a brief discussion on heat and heating, delivery of the waves to the vessel, some safety and control features, and I'll go over an industrial cooking vessel, large scale, and over its features and how products can be processed, and then conclude and have a few minutes for question and answers. So misconception number one, everyone thinks that metals in microwave will cause arcing and cause fire. That's not entirely true. Microwaves can actually be applied to metals as long as the metal is non-magnetic. Metals like aluminum, brass, copper, stainless steel, and the like. So here we want to demonstrate a non-magnetic stainless steel metal. As seen, really nothing happens. Also, to show why metals arc, we should actually discuss how much power is going into the microwave and how much load is available. So if I put a flat sheet of aluminum foil in the microwave and run it, I'm just going to run it for 5 seconds, and there's no arcing taking place. Now, if I put a crumpled up aluminum foil, we'll see that there is a problem. And this is something that really could damage the microwave because there's no load there other than just basically air and this aluminum. There are sharp edges, there are gaps, and definitely we're going to have arcing issue. Now, if I put the same aluminum foil in with a glass of water next to it, because water now acts as a load and couples with microwaves, there shouldn't be any problem. And so we have to understand why there is arcing. Typically, there's a mismatch of the amount of power and the load that is in the microwave. In industrial microwaves, of course, we're able to match the load with the microwave power. The misconception number two is that we think that microwave magnetrons have an antenna, and the antenna sends the microwaves into the cavity or the cubicle chamber we cook. So here's the microwave antenna, but the microwave antenna normally is attached to a waveguide, although this is a short waveguide, about 30 millimeters. And if you look inside your home microwave, you see that the waveguide is normally covered with a plate. And so there is a third misconception, and that is that microwave ovens have to be cubicles. So we have industrial microwaves that are cubicles with waveguides, and we have home microwaves. This is the home microwaves that we just used for testing the aluminum foil. And since there is actually a waveguide that sends the waves into the chamber, so the question would be, why not transmit them away from magnetron? Why not send the waves through a waveguide outside of the cubicle chamber? In fact, we have done that. We have a video that is on the YouTube where the microwaves come from the magnetron, and we attached it to a different chamber, because once we can send the waves out, why do we need to have cubicle chamber? Theoretically, then we can have round or cylindrical chamber. The same thing happens with large scale microwaves. We have a cylindrical cavity, and we have microwave waveguides that deliver the waves there. Another misconception is that water is the best absorber of microwaves in cooking process. Well, water is very strong with surface coupling. Now, we have done years of product development with vegetable oils, especially soybean oil, to process greases and lubricants with microwave. And surprisingly, oil, although it doesn't have a strong surface coupling, it has deeper penetration with the microwave and actually heats better. So we're going to run a couple of tests here quickly. One, we're going to test the water in 4 minutes, and then test oil alone in 4 minutes, and then test oil and water next to each other, just to make a point here. So here's the quantity of water in a container, and we have an identical one for the oil. So the temperature initially is about 15 degrees, and we start the microwave, and I will advance it so we don't have to wait 2 minutes for this to run. As we are advancing that, we come here until it's ready to wrap it up. And now if we test the temperature, first we test it quickly, mix it, and then test the temperature. Temperature is 56 degrees centigrade in 2 minutes. Now we go and run it again for 2 more minutes. And again, we advance it quickly. And now the temperature is 88 degrees. So we're going to do the same thing with oil here. And this time, channel 2 is going to show the temperature for the oil. Originally, it is at 14 degrees, 14.5 degrees. And we'll put it in the microwave and run it. And now the temperature is 67 degrees in 2 minutes, which is considerably higher than what we did with the water. Now we're going to test it again for 2 minutes. And I think we'll make the point that the change in temperature is dramatically different for the vegetable oil versus water. These are same quantity, same mass of the liquids, same container, and same microwave. And now the temperature is actually 117 degrees centigrade, which is about 40 degrees higher. Now we're going to put these two next to each other and run it for 5 minutes to show what happens, which is counterintuitive. So we test these, we run them. We mix the water and the oil and use their respective fiber optic temperature sensors that very quickly tells the temperature. And here's the surprise that water is at 82 degrees and oil at 63 degrees, which we saw earlier that the oil heated much faster. So sometimes we have products like broth here that is a mixture of oil and water. This is what happens now. We've got the two products mixed. So you can imagine water boils at 100 degrees, oil can boil at much higher. And in some cases, especially in this case, because there is no actual mixing taking place, we could have nucleate the water molecules under the oil. So when we want to test this, as soon as the mixing begins, the water will boil because the temperature now is over 100 degrees, and you can see how much foaming takes place. This could be actually dangerous at home because it could spill over, and we can see the temperature is over 100 degrees here. So there are a lot of different synergies that take place when we heat products. And luckily, microwaves allow us to lock into molecules of the specific product. In fact, at some point, we should easily be able to have selective reaction within vessels by targeting specific products. Here's when we were heating the oil, we took some infrared pictures of them. You can see at 22 degrees, everything is cooler. But even when we heat it up to 141 degrees, there are a certain amount of the fatty acids within the triglycerides, the saturated versus unsaturated fats that are still not completely melted. These all help once we understand it to design a system that will be useful for all sorts of applications. We also know that some vegetables, if they have water in them, once you put them in the water would couple faster and gets hotter faster. Okay, very quickly, I need to talk about heat itself, which is really equal molecular motion. When we heat something, we are not adding heat per se to substance, we're increasing its molecular motion. Once we understand this concept, microwaves become a lot safer and easier to understand. So once our hand approaches a very hot object, the hot object has very fast moving molecular motion. Our hand skin doesn't have as fast moving. So when they get together, the molecules of the heat impacts the molecules of the skin and makes it go faster. And of course, the nerve endings sense that and we feel the burn. The same thing could be the opposite. At cold temperature, we can have frostbites because now our skin is moving faster, the molecules, and then the air temperature has a slower moving molecules, and we have the opposite effect. So we have to understand that heating is really increasing the molecular motion of the molecules, and that is why microwaves are so much more efficient, because microwaves directly excite the molecules of the products to heat, whereas in conventional steam heating, we have to first create the heat, create the steam, transfer it to the jackets, heat up the walls, and then transfer it to the interior of the product, to the product inside the tank. And that is not very efficient. Kilowatt microwave generator, and they all have similar components. So when we open this inside, we have 480 volts coming up in the US voltage, and basically some controls and some transformers, because we have to increase the voltage in order to generate the waves. So this is on the other side where we have the transformers, and then we have a set of diodes or rectifiers that gives us DC, and the magnetron that generates the microwaves is right here for safety. It has a shield on it. In order to better understand it, I have another microwave generator. We open this one and take a look at it as well. Again, it has a incoming 480 volts that comes in, a transformer that converts the 480 to 15,500 degrees, a set of rectifiers, a magnetron, a circulator that sends the waves out into a waveguide that then we can put to use. The circulator also redirects the reflected microwaves into a water load so as to prevent damage to the magnetron. Here is a complete microwave system with a 500-gallon vessel. And we're showing this because it's sitting on a 6-foot by 6-foot skid that can be shipped in a container. And we have the principle of plug and heat, because once you get 480 volts electricity, within a day, we can have this thing operational. We need a chiller to cool the magnetron. So the chiller sends the cooling water to the magnetron. This is a 100 kilowatt microwave. And because it's on, we will want to do a leakage test on it. I also wanted to show an old microwave system. The first one we started in 2010, and you can see the waveguides running all the way. In this case, the waves are going into the vessel from the top. There are some safety instruments that we use. We have a handheld microwave leak detector. We have temperature sensors that close the loop. We have a wall mount leak detector that will sense any leakage in the air or in the ambient area. We have arc detectors and magnetic switches for the microwave door that in case it's not closed, it will not let it run. If someone forklifts the waveguides and breaks the waves, the wall leak detector will sense it and will stop. And so we're going to start the machine or the microwave, so we'll do a quick check, but let me just walk through where the waves go. Here's the waves comes out of the microwave. We have a load, which the circulator uses for reflected energy. The power goes into the vessel. And normally, this area is covered for washdown purposes, but we have it open. So the waves go through a patented window. We have 2 windows on the vessels. In this case, we're just using one of them. So here we're going to start the microwave, and we want to run just about 10 kilowatts of microwaves. And the reason being, we want to show that when you are applying microwave power, you'd also get some reflected power. In this case, we can see on the 10 kilowatt, we're getting about 7 to 10% reflection. But we can also tune the microwave power that's going into the vessel. In this case, we have already tested this, so we know that if we wanted to tune this, we can go to 275 here. And now we're going to run this again. You can see that now the reflection is 0.4 on a 10 kilowatt. In fact, we can actually bring this to near zero with tuning, but right now for this demonstration, we have it at 0.3 to 0.4. Our vessels do not use propellers or mechanical mixers, although that's possible to do. So we've got 4 jets. These jets actually can be rotated to have the motion. We can have circular motion. We can have 2 jets go one direction, 2 jets go one direction. We can have chaos created, or we can have smooth mixing. At this time, there is no mixing going on, so we're going to turn the pump on. Right now, it's sitting on 30 hertz. We start, the VFD is 30 hertz. We start the pump, and we check the mixing. There's some gentle mixing at 30 hertz. Now we're going to go and we're going to change this now to 60 hertz, the maximum speed, and see the motion of water. So this would be a lot louder. And now we can see that we have some very strong motion of the water. And we also have a 5th jet or return line that creates a 5th entry into the vessel in case we want to get better circulation. We've run numerous tests on these, and in this case, we are at 80 degrees centigrade in the tank, and we can see the circulation lines are at about 73 degrees. These are not insulated at this time for demonstration purposes, but once they are installed in the plant, we'll have them insulated. With that, I'm going to conclude this particular presentation. We have, as I said earlier, 10 of these webinars. And during these webinars, we're going to cover magnetron-based microwave generators, solid-state generators, and we're also going to discuss the safety, efficiency, and economic benefits of microwaves. We have a showroom. During our 2-day workshop, we actually get to try every one of these. We have heat exchangers that are used for microwaves, with microwaves for retrofitting existing systems. And all of those will be discussed during the next webinars. We have a few minutes for question and answers, and I've already got a question here asking about, how practical are microwave waveguides inside a sanitary food processing environment? This is a very important question. Waveguides are typically made of aluminum or copper, and they are sometimes, or most often, they're painted as well. We know that these are not very much encouraged in the food industry, so WAVEtek has basically embarked on the idea of using stainless steel waveguides. So we have waveguides that are either 316 or 304 choice for use, so they can be power washed for cleaning and wash down. One other aspect to the waveguides is that there are advances in microwave generators nowadays, and these advances include the development of what is called a remote magnetron head, where the magnetron head itself is installed on a short waveguide attached to the vessel. And from there, cables run into another place away from the washdown area and will be attached to the controller. So in that case, it's really the best of both worlds. We're going to have microwave generation and cooking vessels without the waveguides overhead, and in the way making washdown a lot easier. We have time for one more question. And any question that we don't get to answer, we will answer later on. And since this webinar is recorded, it'll be posted on our website. The second question is, are magnetrons considered consumable components, and how does that affect long-term economics? Magnetrons are considered consumables, and it depends on how extensively we use them. For example, on 100 kilowatt microwaves, we normally try to use it at 90 to 95 kilowatt and not at max 100. And in the past, when we ran a 75 kilowatt microwave 3 days a week to make lubricating grease, we ended up running it for about 2,000 to 3,000 hours before we had to change the magnetron. Magnetrons are reasonably inexpensive, but like the light bulbs or vacuum tubes, they get tired and they don't generate as much electrons when high voltages are applied to them, and they need to be replaced. The good news is that although expensive, there are solid state microwave generators that are coming online. Those, just like the current solid state televisions, they can run 50 to 100,000 hours. They are very expensive, but at this time, magnetron-based generators can be used effectively, and depending on the intensity of use, they have to be changed every so often. But we're advancing rapidly, and I'm sure in time, the prices will be more economical for the solid-state microwave generators. With that, we're at the end of our 30-minute talk. We appreciate everyone attending. We'll send invitation for second through the 9th through the 10th webinar, and we'll encourage you that if you have an interest to get hands-on experience with microwave generation and food processing or other industrial product processing, to participate in our 2-day workshops. We also invite people who want to actually test their products to call us. You can send your product here. We can test it in a laboratory scale, 15 or 20 gallons. We can live stream it for you during the process. You can see the whole show in a live situation, or you're welcome to attend and basically run some tests in our facility. We'll also have rental units for people who want to rent a laboratory scale unit to try it in their own shop and compare it with their existing systems. With that, I thank everyone for attending, and we'll say so long.